Okay, thanks for Ning's introduction about motivation, scaling law, and visual transformer. Now we know how to process image with the transformer. Next, I will continue to cover more details about diffusion transformer design. Adaptive layer norm. We already know batch norm and layer norm. Both are used for standardized data to avoid too much shift during forward propagation among layers. Batch norm calculates the mean and standard deviation on batch dimension because of the limitation of a GPU RAM. Sometimes we can only use the small batch to train, which causes instability. To solve this problem, layer norm was proposed to calculate mean and standard deviation on feature dimension. Both normalization can be considered as the oh, multiply scale coefficient gamma and plus shift term beta. So adaptive norm try to calculate gamma and beta with the neural network rather than calculate them with the pre-given formula. Here is the architecture figure in the paper, and I draw a more detailed one to illustrate the model design. We focused on the condition injection part. Here, in diffusion model, we commonly have the two condition parts, one for diffusion time step and another is for the normal uh, condition. Both of them can be represented by a vector. Here in this paper, the author add these two vectors the element-wise and then use the linear layer to enlarge the dimension from d to 6 times d. We split them and get 6 vectors, each with the d dimension. These 6 vectors will be used at the scale coefficient and shift term later. This part is the patchifying process introduced by my teammate. After patchifying and adding positional encoding, the tensor changed from the image grid-like data to our familiar form in language process. Then it will be added. It will be fitted into transformer. Here, after layer norm and before multi-head self-attention, we implement scale and shift operation with the first and second vectors we calculated just now. Notice here we add we need to broadcast along the length dimension. After multi-head self-attention, we use the third vector alpha to do the same scale operation. Follow the same way before and after feed-forward layer. The last 3 vectors are used to scale and shift. This is so-called adaptive normalization. In, in diffusion transformer, we also initialize the final layer width and the bias with 0. In this paper, model with the adaptive normalization and zero initialization is denoted as ADA ln 0. The essence of the diffusion transformer design has been introduced completely. Next, I will cover some experiments in this paper. Before that, I will back up some knowledge about model complexity. How to measure model complexity? Number of parameters is a choice, but not precise. For example, residual connections that won't incur additional parameters but increase the computational complexity. An alternative way to measure model complexity is the FLOPS. This unit is to measure how many operations that are required to run a single instance of a given model. Here is the table showing how many operations per token in transformer architecture. In experiment part, there are 3 questions need to answer. First, which model and conditioning design is the best? The author compared different conditioning design in context, cross-attention, adaptive layer norm only, and adaptive layer norm with zero initialization. As illustrated here, the adaptive norm and zero initialization perform best. So in the following experiments, adaptive layer norm and zero initialization is the default choice for diffusion transformer. Also, the author did the experiment to compare convolution-based model. Here, ADM, LDM is the both are convolution-based model. The bubble area indicates the slopes of the diffusion model. In this experiment, we can see diffusion transformer also have a better performance and with the similar model complexity with convolution-based model. The second question is the scaling property still preserved? The author did 2 sets of experiment, holding patch size constant and holding model size constant. The upper row represents the experiment with the holding patch size constant. We can see the performance improves with the model complexity grew up. The lower row represents the experiment with holding model size constant. We can see the performance also improves with the patch size decrease. Decreasing patch size equals to increase the dataset. The author also visualized the scaling property. Horizontal change is about the model size, and the vertical change is about the patch size. We can visually see the scaling properties that's the generation result getting better with the increase in model size and the dataset. The author also did an experiment to illustrate flops is a critical factor for model performance rather than the number of parameters. For example, here, B8 has more parameters than S4, but B8's performance is worse than S4 since the patch size is larger, meaning that the dataset is the smaller than S4. Another example here, S2 has the less parameters than B4, but the performance of S2 is equal to B4. Why? Because the S2 with the smaller patch size leading to more computation for one image.